In our previous lecture, we have studied the basic functioning of a normal voltage transformer, which is electromagnetic type, and we have also seen the normal functioning of a CCVT or the coupling capacitor type voltage transformer. Now we also saw that there can be a phenomenon of ferroresonance if there is some series capacitance and inductance in the circuit, and that inductance should be saturable or non-linear type. Okay, now let us see what happens if we overload a CCVT. Usually, as we have seen in our previous lecture, that there is a specific amount gross power available from the CCVT to the burden. Now what will happen if I overburden it? Let us see. The equivalent circuit diagram of CCVT was drawn in the previous lecture as there was a source E Thevenin, the Thevenin equivalent capacitance, it was equal to C1 plus C2, the tuning reactor including the leakage reactance also, the shunt branch of the transformer, and this is the burden impedance of any equipment. So this is the equivalent circuit diagram of a CCVT. Now usually in a voltage transformer or a CCVT, overburdening means that we are drawing more current from the circuit. Okay, so if I neglect the effect of this shunt branch, because it can be neglected, so I will remove this. After neglecting the effect of shunt branch, what we can see that overburdening means that this ZB or the burden impedance is being reduced. When this ZB is reduced, I will increase, that is the current will increase. Okay, now let us take the worst case in which ZB is equal to 0. Now when this ZB is replaced with a short circuit like this, what will happen? We will see that this ZL and ZC have come in series. Now we have already seen in our previous lecture that they are designed such that omega L is equal to 1 by omega C1 plus C2. So in this case there will be a resonance in the circuit. Now we have already known that during resonance there will be magnification of the voltage also. Now there are spark gaps available in the CCVT. Because of this over voltage appearing, these spark gaps will start sparking. Continuous sparking will start. Although there will not be any much damage to the CCVT, but these spark gaps may get permanently damaged. Okay, so we should avoid the overburdening of CCVT for a continuous duration. For some transient duration it is okay, but for continuous duration this spark gap will get damaged. Okay, so this is the effect of overloading on a CCVT. Now let us see briefly about the transient response of a CCVT. Okay, that we will see after erasing this. Usually during a fault, what happens to the voltage? The voltage usually collapses on the faulted phase. Okay, so as compared to the current transformer, the current usually increases in the fault if there is shunt fault, and the voltage usually drops. Okay, or the voltage collapses on the PT. If the fault is very near to the PT, then there will be total collapse of the voltage. Okay, now this is the equivalent circuit diagram of a CCVT. Here this is being charged by E Thevenin, which is nothing but some E max cos or sine omega t plus phi. Okay, now let us say there is a fault at t is equal to 0. So how can we simulate this thing? We can simulate if we energize this circuit with a source which is having characteristics like that Et is equal to minus of E max cos omega t plus phi for t greater equal to 0 and 0 for t smaller than 0. Okay, so I can simulate the fault by energizing this circuit using this ET. So this is the normal source voltage which is available on the PT, and this is the additional source voltage which we are going to apply to simulate the fault. Now the calculation can be done using Laplace transform, and we can simplify it further by neglecting the effect of this RC and by taking this burden just to be purely resistive. However, still the calculation will be very cumbersome. So instead of calculating what we practically do, we simulate it on some software like MATLAB or some other software. Okay. Now it is seen that the transient response of Ccvt can be drawn like this. When there is a voltage collapse, usually the fault occurs due to insulation failure. Now insulation failure usually will happen at the maximum point of the voltage. Okay, so let us say this is the voltage. So if any insulation failure is going to happen, it is most probably going to happen at this point, and voltage will get collapsed at this point. Now it is observed from simulation as well as practical readings that the Ccvt response is very fast damped, okay, when there is a voltage collapse from the voltage maxima. However, when there is a voltage build up, like now let us say I reclose the circuit, okay, this is some voltage wave going on, and now I reclose the circuit here. Okay, now it is seen that the response of Ccvt is little bit one way or one sided. That is, it is damped, but it damps gradually. Okay, and it can sustain some value on one side of the values. Either it can be positive or negative. Again, it is a damped response only, but it can sustain up to some point of time and it is not going to cross 0. Okay. However, when this is voltage collapse from the Vmax, the response is very fast damped. This is when voltage build-ups. Okay. Now, what will happen to the relays which are connected here? These relays will see improper voltage. This is not the actual power system voltage, so they may not work properly. Okay, so what is the remedy? The remedy is that we can desensitize or add a deliberate delay. Okay, that is, relay should act after some delay so that the transients can die out. Okay, however, it is having some negative consequence, especially for instantaneous relays, especially for the distance relays of the zone 1 protection. We will see later what are various zones of protection on a distance relay. So zone 1 protection distance relays which act immediately, if they are given some deliberate delay and they will need voltage value and current value to find Z. So if they add delay here, then they may not work instantaneously. Okay, so we cannot give delay to all kind of relays. So what is the remedy? Now some relays have some kind of memory element. Okay, so this memory element stores very briefly the voltage levels of the power system. Okay, so this instantaneous response can be taken from that. However, for the situations when there can be reclosing of the circuit breaker, then that memory will die out very fast. Okay, because since we cannot manipulate the various values of the system, otherwise there will be no use of measurement. So this memory element should delay very fast, and it delays very fast. So it decays very fast. So during reclosing, this part will create problem for the response of the relays. However, practically it is seen that not only these transient responses are there, the frequency of these transient responses is different from the normal frequency of the system. Okay, there can be subnormal frequencies or there can be harmonical frequencies. Okay, so because of this there can be other problems. However, it is seen that if the normal frequency voltage value is greater or equal to 5% of the normal, then the response of relays is quite satisfactory and we do not face any problem. So practically these transient phenomena do not create much problem if the normal frequency voltage is at least 5% available there. So our devices will work properly and the transient phenomena will not affect the response of the relays. Okay, so usually in practice there is not much problem if we design the system properly. Now here what I have done, I have drawn a circuit in which I have drawn 3 potential transformers in delta connection on the primary as well as secondary. So this is phase A conductor, phase B conductor, phase C conductor. Now what I have done is I have connected burdens also in the delta with burden impedance ZB is equal to 50 ohm angle 0, that is purely resistive burden is there, and the leakage impedance or the equivalent total leakage reactance or impedance of the transformer, the PT on the secondary side, this is the secondary side, is given as 1 plus J5 ohms on the secondary side. Okay, now we are also told that the nameplate PT ratio or the nominal ratio is 69 kV over 120 volts. It comes out to be 575. Now what we are asked? We are asked to find ratio correction factor. Now what is the meaning of ratio correction factor? As you might have seen in my previous lecture where I have defined this term, it is nothing but a factor which should be multiplied with, this is the, let us say, nominal ratio, and this is the factor. If I multiply them, then I should get the actual ratio, transformation ratio. Okay, so this thing is the nominal nameplate ratio and this is the actual ratio and this is the ratio correction factor. Now how to determine this thing from the given data? Now you can see that the system is actually balanced. ZB is same and ZL is also same for each phase. Okay, so if I want to do the calculations, I can do the calculations on per phase basis. So if I draw this figure on per phase basis, what I will draw, it is EAB0. What is EAB0? The voltage across or the voltage induced in the secondary of the voltage transformer on phase AB. Okay, this will be EBC0, this will be ECA0. Okay, now the voltage across burden is EAB EBC, ECA after the drop in the leakage impedance. EAB 0, this is ZL, this will be ZB, and the voltage across the burden will be EAB. Okay, now since I am going to work only on the secondary side, so what does it mean? It means that the factor which I should multiply with EAB0 should give me EAB. Then this factor will be the ratio correction factor. Okay, that is, if I multiply this factor with the nominal voltage, then I should get the terminal voltage. Okay, so this is the only definition of a ratio correction factor, and since I am just working on the secondary side, that's why I am not taking any other turns ratios or any other voltages. Now this IA dash will be here and this IA will be here. Now since the circuit is balanced, then on the per phase basis we can clearly see that IA dash is equal to IA. Okay, and I can also see that EAB is nothing but EAB0 divided by ZB plus ZL. It will give me the current into ZB. It will give me the EAB. Okay, so you can see that EAB is equal to ZB over ZL plus ZB into EAB0. So this thing is the ratio correction factor, and this will be the same for each phase. So you can see that for each phase voltage transformer in a balanced system, even if it is delta or star, we could have also solved this with this equivalent star also. So we can see that the ratio correction factor will be same for each PT. Okay, and on putting the values, it will come out to be 50 over 51 plus J5, and this is the ratio correction factor. Okay, so in this way we can solve such kind of numerical example and we can find the ratio correction factor. Now here is one more important point to note, that the burden on each PT is same. You can see that voltage induced is same, current is also same, so VI burden is same on each PT. However, in the next slide we will solve a numerical example in which we will see that in an open delta system the burden is different for each phase and also the ratio correction factor is also different for each PT. Now let us see the next numerical example. This numerical example is little bit of higher level. However, it will give a general method to proceed with various numerical example involving open delta connection. Now here what I have done, I have shown two potential transformers connected in an open delta, or one of the delta has been removed. Okay, so as we know that the sum of line voltages is equal to 0, so only two line voltages are required and the third one can be taken out from the relation. Okay, so only two PTs are there. However, three burdens are included: phase A, phase B and phase C, and all the burdens are again equal to 50 ohm. On the secondary side, the leakage impedance of the transformer is given as 1 plus J50 ohm on the secondary side. Then PT ratio is 69,000 over 120 or 575. Okay. Now we are asked to find again the ratio correction factor for each phase. Okay, because it is an open delta or the broken delta connection, so it is it is, a little bit obvious that ratio correction factor might not be equal for all the phases. Okay, let us see what is the issue now. This is the relation which is there for EAB plus EBC plus ECA is equal to 0. It is valid for line to line voltage across these burdens, or even for the conductors. Okay. Now, what is the difference here? EAB0 is the voltage induced on the secondary side of the PT, and EAB is the voltage on the terminals of this PT or the across this burden. Similarly, EBC0 and EBC. The current through the burden is IA, IB and IC, and this is voltage ECA, and the voltage across these two will be ECA. Okay. Now we know that EAB from this circuit, this EAB simply can be written as EAB0, this voltage minus drop in this leakage reactance, which is IA-ZL. This is what I have written here. Okay. And further we know that IA-, this is IA- is nothing but IA minus IC. Now what is IA? IA is nothing but EAB over ZB, and IC is nothing but ECA over ZB. So this is what I have written here, EAB minus ECA over ZB. Now I have used this relation ECA is equal to minus EAB minus EBC to get IA- is equal to twice of EAB plus EBC over ZB. Similarly, I can write for EBC. EBC is this. It is nothing but equal to EBC0 minus IB-ZL. And IB- similarly can be found out as twice of EBC plus EAB over ZB. Now, what I will do, I will utilize these two relations derived from these two steps. Okay. And I will try to find the value of EAB in terms of EAB0 and some factor. And that factor will be simply the ratio correction factor for this PT or for this phase, for EAB phase. Okay. Now, I have solved this by putting the value of IB dash, this IB dash here. So EBC is equal to EBC0 minus twice of EBC plus EAB over ZB into ZL. Or on further solving, I can find that EBC is nothing but EBC0 minus ZL over ZB EAB into 1 over 1 by 1 plus 2 twice of ZL over ZB. Now, since I want to just find EAB0 and EAB relation, so I should eliminate this also, because in EAB0 there is EBC, and this EBC can be found out from this, but still it is having EBC0. So I will have to replace EBC0 using this relation. For a balanced system, EAB is equal to EBC into e raised to power j2 pi by 3 or angle 120 degree. There is the phase difference between two line to line voltages. Okay. So using this and further solving, I can find that EAB is equal to EAB0 and into this factor. Okay. So this is nothing but EAB is equal to EAB0 into RCF1. So this is the ratio correction factor 1 for this phase PT. Okay. Now similarly on the same steps, I can find that EBC is equal to EBC0 into RCF2, where RCF2 on solving, it is left as an exercise to the student. It will be ZL over ZB E j2 pi by 3 minus 1 plus twice of ZL over ZB divided by this same factor, this factor, ZL over ZB squared minus 1 plus twice of ZL over ZB squared. Okay, but here is the difference. Here it is E minus j2 pi by 3. Here it is E plus j2 pi by 3. So this is the difference. So this is RCF2. This is ratio correction factor 2. So EBC is equal to EBC0 into RCF2. So this is the second ratio correction factor which we have found. Okay. Now how to determine the ratio correction factor for the third phase? ECA is equal to ECA0 into RCF3. How to find that? Now we know that ECA can be written as minus of EAB minus of EBC. Okay. So I can use this relation here. So RCF3 is nothing but ECA over ECA0. Okay. Is equal to minus EAB minus EBC over ECA0 over ECA0. Now we can see that ECA0 is nothing but EAB0 E minus 4 pi by 3. Okay. And ECA0 is equal to EBC0 minus 2 pi by 3. J will come here. Okay. So this is the relation which we have. So I can replace ECA0 with EAB0 and EBC0 like this. So RCF3 ratio correction factor 3 will be equal to minus of EAB over EAB0 into E minus J 4 pi by 3. It will be taken on the numerator side. And what is this? It is nothing but RCF1 minus of RCF1. Similarly, it will be EBC over EBC0 EJ2 pi by 3. So we can see that RCF3 is nothing but minus RCF1 EJ4 pi by 3 minus RCF2 EJ2 pi by 3. And we can see that all the ratio correction factors are different. These are not same for any of the phases. So you see that even if we take totally balanced system, even then the burden seen by the various PTs will be different and the ratio correction factor will also be different for all the PTs. Okay. Now in the next slide we will just discuss little bit about the current technology or the new advancements in the voltage transformer technologies. As we have seen in the study of current transformers, the latest developments in the technology, similar technology can be utilized for potential transformers. Let us see how. In the Ccvt, there is a capacitor stack where it is the coupling capacitor and this is the auxiliary capacitor and this is a reactor which is seen showed by the power frequency voltages, and this is the system voltage. Now you see that the current through this capacitor stack will be depending upon the voltage, okay, or this current will be depending upon the system voltage as well as these capacitances. Now these capacitances will be taken by design, okay, so current will be just proportional to the voltages, okay. Now this current can be measured using those Rogowski coil or other phenomena using magnetic or magneto-optic CTs, which will be working on the phenomena which we have seen in our previous lecture, where the polarization plane or polarization of an electromagnetic wave is changed by the magnetic field of a current flowing through a conductor. So if I put a optical fiber block here with optical fiber over it, and I send a polarized light through this, and I receive the light here, then the polarization will change and I can detect the deviation in that, and that will be proportional to the magnetic field, and that will be proportional to this current, and that current on integration will give the voltage. Okay, since I is equal to C dV by dt, instead of writing proportional, I will write it some function of V. Okay, so if I integrate this, I will get some signal equivalent to voltage. So in this way, I can utilize the technology of the same thing which we have studied in the advancement of CTs. However, there is a problem. What is that problem in advancement of these PTs? Is that there is somehow a connection required between the power voltage and the ground. So insulation requirement is still there. So the technologies, no matter what we involve, if we cannot eliminate this connection, the insulation requirement will not reduce. So expenses will not reduce, it will still be a costly solution. However, since these devices are linear and do not suffer transients, so I believe in the upcoming days or decades, these will be a norm. Similarly, there is a technology called Pockels cells. These are also working on the similar phenomena of the plane of polarization change of an electromagnetic wave. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.